Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we will discuss some more basic definitions. In the last lecture, we discussed the idea of basis vectors, Broadway lattice, non-Broadway lattice, and the idea of unit cell. Now we will move forward. So first, we will discuss now primitive versus non-primitive cells or unit cells. So first, let us discuss this idea. In the last lecture, we discussed the idea of a primitive cell. It is sometimes more convenient to deal with a unit cell which is larger and which exhibits the symmetry of the lattice more clearly. And to illustrate this idea, let me draw a figure of a Broadway lattice. So I will draw a figure first, then we will move forward. Let me use another color. So this is our figure 1. So let me show some basis vectors first. I think I will use another color for that. This is A, this is B, then what do you do? Let this vector be A1 and this one be A2. So this is a figure of a Broadway lattice. Let me check it. Yes, it's okay. So you can see vectors A1, A2 can be chosen as a basis set. For this lattice, we can choose this A1 and A2 vectors as a basis set. In which case, the unit cell is a parallelogram S1. Which parallelogram? This parallelogram. I shade it. This is S1. Right? So if A1 and A2 are taken as basis vectors, then S1 is the unit cell, right? However, the lattice may also be regarded as a set of adjacent rectangles, where we take vectors A and B as basis vectors. The unit cell is then the area S2, that is this area. So if A and B are taken as basis vectors, then S2 is the S2 is the unit cell, right? So you can take A1, A2 as basis vectors for this Broadway lattice. Then this parallelogram S1 is the unit cell, or we can take A and B as basis vectors. Then the area S2 is our unit cell, right? Now area S2 has one lattice point at its center in addition to the points at the corner. You can see S2 has a lattice point at the center in addition to the 4 points at its corners, but S1 has no point within, only it has points at the corners. So S2 cell is a non-primitive unit cell. I hope you got the point. In primitive cells, the lattice points are only at the corners but not within. So S2 is a non-primitive unit cell. Now the reason for the choice of the non-primitive cell S2 is that it shows the rectangular symmetry most clearly. Although this symmetry is also present in the primitive cell S1, the choice of the cell somehow obscures this fact, right? Now we need to note something about this. First thing, let me write remarks. First remark is the area of the non-primitive cell is an integral multiple of the primitive cell. The area of the non-primitive cell is an integral multiple of the primitive cell. Now you can see in figure 1, the multiplication factor is 2. The multiplication factor is 2. You can see S2 area is twice this area. You can check. this area is double this area. So this always true that the non-primitive cells have area which is integral multiple of the primitive ones. That means it can be twice, thrice, 4 times, 6 times, 5 times, 6 times, 7 times, and so on. Here it is twice. Second thing, there is no connection between non-primitive cells and non-Bravais lattices. No connection, there is no connection between non-primitive cells and non-Bravais lattices. Non-primitive cell refers to particular choice of basis vectors. It refers to particular choice of basis vectors in a Bravais lattice, right? While the non-Bravais lattice refers to the physical fact of non-equivalent sites, right? So you need to remember these things, don't get confused. So let us extend now our ideas to 3 dimensions. 3 dimensions. Now all the previous statements can be extended to 3 dimensions in a straightforward manner. When we do so, the lattice vectors become 3-dimensional and are expressed by Rn N1A plus N2B plus N3C. We name it first, where A, B, and C are 3 non-coplanar vectors joining the lattice point at the origin to its near neighbors. Let me try to draw this in figure. Anything 3-dimensional is difficult to draw on 2-dimensional page or board. So I will try to draw it So I have like this. We use a color for this. Let me use back. And this drawing is ugly, so let me not draw it. I'll not draw it. So let me draw this figure 2. You can check it in the textbook, you can understand it. It's near neighbors. So we're here. Rn is now the lattice vector in 3 dimensions. ABC are 3 non-coplanar vectors joining the lattice point at the origin to its nearest neighbors or near neighbors. And n1, n2, n3 are a triplet of integers. n1, n2, n3 are a triplet of integers. So they can be 0, plus minus 1, plus minus 2, etc. And whose values depend on the particular lattice point. Now the vector triplet ABC is the basis vector set, and the parallelepiped whose sides are these vectors is a unit cell, right? Here again, the choice of primitive cell is not unique, although all primitive cells have equal volumes. I think I should write it. I said the vector triplet A, B, and C is the basis vector set, and the parallelepiped whose sides are these vectors is a unit cell, And you know, here again, as in the case of 2 dimensions, the choice of primitive cell is not unique, right? Although all primitive cells, although all primitive cells have equal volumes. Remember, in 2 dimensions, we said all primitive cells have equal areas. Also, it is sometimes convenient to deal with non-primitive cells, ones which have additional points either inside the cell or on its surface, right? Finally, non-Bravais lattices in 3 dimensions are possible and are made up of 2 or more interpenetrating Bravais lattices, as we discuss it in 2 dimensions. Let us move to next thing. Our next thing is the 14 Bravais lattices and the 7 crystal systems. Let me underline it. The 14 Bravais lattices and the 7 crystal systems. You need to remember, we're talking now in 3 dimensions. There are only 14 different Bravais lattices. Only 14 different Bravais lattices. And this reduction to what is a relatively small number is a consequence of the translational symmetry condition demanded of a lattice, right? In fact, it can be demonstrated that the requirement of translational symmetry in 2 dimensions restricts the number of possible lattices to only 5. So, in 2 dimensions, only 5 Bravais lattices possible. In 3 dimensions, we have 14 different Bravais lattices possible. And this number is restricted due to translational symmetry condition, right? So in 2 dimensions, we have 5 Bravais lattices, and in 3 dimensions, we have 14 different Bravais lattices, right? Now, the number of non-Bravais lattices in 3 dimensions, the number of non-Bravais lattices in 3 dimensions, is much larger. It is 230. The number of Bravais lattices in 3 dimensions in 14. The number of non-Bravais lattices in 3 dimensions is 230. Right? Now let us move to 3 dimensions and Bravais lattices. Now the 14 lattices, Bravais lattices or crystals classes are grouped. The 14 Broadway lattices or crystal glasses are grouped into seven crystal systems, right? Each specified by the shape and symmetry of the unit cell. Each specified by the shape and symmetry of the unit cell, right? Now these systems are, what are the systems? 7 systems. These systems are the triclinic, monoclinic, orthorhombic, tetragonal, cubic, hexagonal, and the trigonal or rhombohedral, right? So we have 7 crystal systems. Underline them. Triclinic, monoclinic, orthorhombic, tetragonal, cubic, hexagonal, and trigonal or rhombohedral. Now in every case, the cell is a parallelepiped. In every case, the cell is a parallelepiped whose sides are the bases A, B, C. The opposite angles are called alpha, beta, and gamma. Let me try to show it in figure. This is A, this B, and this C. Another color. So it's like this. So I have this like this. Then I do this. So here I have a point. Then here one point. Bear with me. So here point. So here I have point. Here point. I hope I will complete it. What remains? This thing. Oh, I have completed it. This is phase 1, 1, 2, 3, 4. The base 1, 2, 3, 4. This another side 1, 2, 3, 4. This front side 1, 2, 3. This back side 1, 2, 3, 4. It's complete. One phase, second phase. I'll make it something prominent. So let me name this figure. This is my figure 2. One phase, how many points I have? 1, 2, 3, 4, 5, 6, 7, 8. 4 and 4 are 8. One phase, second phase, third phase, fourth phase, fifth phase, and sixth phase. It's okay. Now, opposite angles are alpha is opposite angle to A, that is this angle is alpha. Beta is angle opposite to B. So this is beta. And gamma is angle opposite to C. This is gamma. So alpha opposite to A, beta opposite to B, and gamma opposite to C. Right? So we said that in every case, the cell is a parallelepiped as shown in this figure 2, whose sides are the bases A, B, C, and opposite angles are alpha, beta, and gamma. Now we will tabulate these systems and lattices and the appropriate values for A, B, C, and alpha, beta, gamma. So let us move to that table. So I have crystal system. Then I have Broadway Lattice. Then I have unit cell characteristics. So table at. I will. So let me use another color. The first system is our triclinic. Corresponding to triclinic system, we have one Broadway lattice which is simple, which is characterized by A not equal to B, not equal to C, alpha not equal to beta, not equal to gamma, not equal to 90 degrees. Understand it. So in case of simple Bravais lattice, we have all the three edges of the parallelepiped are non-equal and all the opposite angles are non-equal and non-90 degree, right? Let us move to next. Next is ortho, also first we'll write monoclinic. Monoclinic. There are two possibilities for Bravais lattice. One is simple, second is base centered. Go to any textbook to look at these 14 Bravais lattices which we are going to list or characterize in terms of unit cell characteristics. It is difficult to draw them, but you can check them on any textbook or you can Google. So one is simple and second is base centered. What are the unit cell characteristics? A not equal to B, not equal to C, alpha equal to beta equal to 90 degree, not equal to gamma. Check it. So in case of monoclinic, all three sides are unequal. Two angles alpha beta are equal and equal to 90 degree, but gamma is not equal to 90 degree, right? Then we have, let us move to third one with new color, orthorhombic. In orthorhombic, we have four possibilities. One is simple, second is base centered, third is body centered, and fourth is face centered. So what are the unit cell characteristics? A is not equal to B, is not equal to C, alpha is equal to beta is equal to gamma is equal to 90 degrees. So for orthorhombic crystal system, four possibilities: simple, base centered, body centered, face centered, and unit cell characteristics are all three sides are unequal, but all three angles are equal to 90 degrees. Then another crystal system is tetragonal, where we have two kinds of Bravais lattice. One is simple and second is body centered. Body centered. Unit cell characteristics are A equal to B, not equal to C, alpha equal to beta equal to gamma equal to 90 degrees. So for tetragonal, two possibilities, simple and body centered, two sides equal in unit cell, third is not equal, all three angles equal to 90 degrees, right? Then there is another possibility, which is cubic. In cubic, There are three possibilities. One is simple, second is body centered, and third is face centered. What about the unit cell characteristics? A equal to B equal to C, the simplest to remember. All three sides equal and all three angles equal to 90 degrees. Then we have another possibility, another crystal system, trigonal or rhombohedral, where we have only one possibility of Bravais lattice, which is simple. Unit cell characteristics A equal to B equal to C, alpha equal to beta equal to gamma not equal to 90 degree, but all less than 120 degree. Understand it? In case of trigonal or rhombohedral, one Bravais lattice is possible. Unit cell characteristics are all sides are equal. Alpha, beta, gamma, all are equal, non-90 degree and less than 120 degree. Then there is last one. Let me use this color. This is hexagonal. Hexagonal. Only one possibility, simple. And we have unit cell characteristics A equal to B, not equal to C, alpha and beta equal and equal to 90 degree, gamma is 120 degrees. So in hexagonal crystal system, only one Bravais lattice is possible, simple. A is equal to B, two sides equal, third one not equal, two angles 90 degree, third one 120 degree. So let me write the heading of the table. This was system. This is Bravais lattice. And this is unit cell characteristics. Let me move to another page. So this was system, Bravais lattice, and unit cell characteristics. So let us check. One system is triclinic, second is monoclinic. Then we have orthorhombic. Let me number them. So it's first, the second system, then third system, then fourth system, then fifth system, sixth system, and seventh system. So we have 7 crystal systems. Let us count the Bravais lattice. Here we have one lattice possible. Here we have 2 lattices possible. In another system, we have 4. Here we have 2. So here we have 3 possible. Here we have 1. And we have here 1. So let us add them. 1 plus 1 is 2, plus 3 is 5. 5 plus 2 is 7. 7 plus 4 is 11. 11 plus 2 is 13. And 1 is 14. So we have 14 Bravais lattices and 7 crystal systems. Next thing which you need to remember is simple lattice has points only at the corners, right? Simple lattice has points only at the corners. A body-centered lattice has one additional point at the center of the cell, right? Then, and a face-centered lattice has six additional points, one on each face, one on each face. Now you need to remember that in all the non-simple lattices, the unit cells are non-primitive, right? In all the non-simple lattices, the unit cells are non-primitive. Let me write it. In all the non-simple lattices, the unit cells are non-primitive, right? Now the 14 lattices which we have tabulated exhaust all possible Bravais lattices. It has a mathematical proof, but that proof you can check. We are not going to discuss that proof, but you can check if you are interested, or you can Google that proof. This is all for today. Go through all the video lectures and don't forget to like, share, and subscribe my channel. You can comment in the comment box as well. Thank you. God bless you. Assalamu alaikum.